my talk is going to be about how we can use the spectral exponent of the resting state EEG in order to index the presence of consciousness across multiple brain states. I want to begin with a little provocative thought. So try to picture yourself into the body of a dog. Now imagine that you're undergoing anesthesia, and imagine what are you going to feel. What will be your experience? Are you going to have an experience similar to a dreamless sleep, like the dog depicted there sleeping peacefully, or you're actually going to dream about perhaps a wild scenario? We actually have no way to know it, because unfortunately we cannot ask the dog, not even when he has awoken from the anesthesia. So this is the sort of provocative thought I wanted to place forward to you, so that it will serve as a reference question for the talk. Now, if we have patients that cannot respond, that would be a similar scenario in the sense that we cannot use language to communicate. So ideally, the bottom line would be we would like to have a neural marker for the presence of a conscious experience, whether it's externally generated or internally generated. So in this talk, I'm going to convince you that an unresponsive person is not necessarily unconscious, and indeed, as we said, the goal would be to find a brain state index that will be able to disentangle unresponsiveness from unconsciousness. And in the first part of the talk, I will show you that there are drugs that are capable of selectively producing dissociated consciousness or instead unconsciousness. And then we're going to validate the index in sleep and in pathological disorders of consciousness. So, yes, in the introduction part, I will also tell you a bit about what does scale-free mean, and if the EEG has some scale-free properties. I'm going to tell you how unconsciousness affects the EEG, or at least what was our working hypothesis in the beginning. So, with respect to the first part, there are drugs that are capable of producing unresponsiveness, and some others that are capable of producing unresponsiveness and unconsciousness. So, for instance, in this case, by unconsciousness, I mean the lack of any conscious experience, whether internally or externally generated. In one case, it can be produced by xenon, which is a rare gas, and has some interesting properties, but it's also very expensive. So it was used in this case as a particular agent that has different mechanism of action rather than the classical ones. So what it does is it's an antagonist of NMDA receptors, and it increases potassium conductance. So it has this increase in excitability, but at the same time it leads to a prolonged refractory period, so that whenever there is an increase in excitability, the firing rate cannot be sustained and it follows a downstate. We also use propofol, a more classical agent that is potentiating inhibition, essentially. These two drugs produced, according to follow-up reports, a state of unconsciousness. Instead, we use also ketamine, and invariably this agent was giving rise to a state of dissociated consciousness, as depicted in the cartoon. So ketamine is also an antagonist of NMDA receptors, and what it does is essentially to increase this availability of synaptic glutamate, and it increases as well these neurometabolic factors associated with excitability. So much for the drugs. Then I'm going to give a bit of an overview of what I mean by scale-free, and then we see how this is relevant for the EEG. So by scale-free, I mean that there are similar properties across scales and zoom, and that there is no characteristic scale, and that finer details are nested in larger ones in a recursive fashion. So we know that many systems have a scale invariant distributions over at least some decades. And for example, earthquakes, web citation, and money. So I'm going to give an example about it just to make sure everyone is familiar. So very few people own a lot, some people own something, and most people own little or nothing. And this has been made particularly famous by We Are the 99% movement. So what we're interested in is the slope of the decay in a log-log axis. And the steeper the decay, the more money goes to a smaller amount of people in this example. So I'm just going to give you some examples of how brain dynamics have been shown to be scale-free, to have scale-free properties. For instance, in the no degree of fMRI networks, in the amplitude modulation of EEG fluctuations and fMRI fluctuations, on how oscillations synchronize, the periods is scale-free distributed, and the temporal and spatial distribution of LFP peaks, and also at lower scale there have been scale-free properties in neural spike trains and neurotransmitter release, and many others. So we're actually going to look to something that is far more simple. It's just looking at how power spectral density is distributed. So as you know, we can decompose a time series into its spectral representation via Fourier transform. And the typical example is that we, from a neural recording, is that we have large power at slow frequencies, some power at middle frequencies, and small power at fast frequencies. That means that there is a similar power frequency ratios as we change the frequency band of interest. There is no characteristic frequency, well, at least in the background. We'll see more about this. And faster frequencies are nested in slower ones. So by these three properties, we can say that the EEG has a scale-free property. So the steepness of this decay is indexing how the relationship basically between power and frequencies, and how steeply the power spectral density decays. So for some of you that are familiar with sound processing, these examples might be familiar to you. Otherwise, it's just as a reference to know that signals can be prototypically described pertaining to one of these categories, whether depending on essentially the appearance, if it's hairy or if it has a slow fluctuation. Basically, there's some variations, and we have seen that EEG has and ECOG have a power spectral density that has a scale-free background, and it can be described by a power law. Here, beta would be the index, and it's typically less than 0, and typically it will be somewhat between pink noise and brown noise. And beta will actually tell us how steep the PSD decays over frequencies. And a steeper decay means that there is a smaller contribution of the fast wave relative to the slow one. So the steeper, the more we go towards brown noise, and the flatter, the more we go towards white noise, essentially. So here it's just to show you how an EEG looks like if we artificially change the steepness of the power spectrum. So in green, we see a typical wakefulness time series with alpha burst. And on the right, in green as well, you see its spectral representation. And as I artificially change the background on the spectral representation and then reverse the Fourier transform and get it back into the time domain, we can see how slow waves start to appear as the PSD becomes steeper. And the spectral, basically as the spectral representation is steeper, the more the signal tends to look smoother and with large amplitude slow waves. So unconsciousness has been historically related to a process called EEG slowing, meaning that the characteristic oscillation from high voltage tends to go to, and fast frequencies tend to go to, from low voltage and fast frequencies tend to go to high voltage and slow frequencies. And this has been shown both in sleep and anesthesia. And so when we look at the PSD, we see that essentially there is an increase in slow oscillation and a decrease in fast oscillation. But this is something that can be represented by a simple parameter that is indeed the steepness of the PSD in log-log scale. So, does the power spectral density of the EEG steepen in unconsciousness? Yes, there seems to be some preliminary data about it, at least in sleep and in ECOG, in the human, and it seems that there is a decrease across the non-REM stages, with the lowest exponent, so the most negative exponent being in slower sleep, so the steepest spectrum appearing in slower sleep. And then, interestingly, it seems that in the one subject that has been studied by Liu He with the ECOG, it seems that the REM case is in the frequency of interest above 1 Hz. It seems to be pretty much similar to the awake, with the results of slower sleep being confirmed. So here's our hypothesis that the PSD of the EEG becomes more steep during unconsciousness. So a little bit of summary. We have used these 3 different drugs in healthy participants to yield unconsciousness or a state of dissociated consciousness. EEG is being shown to be scale-free in the sense that it has no typical frequency, that small waves are nested within larger ones in recursive fashion. And our hypothesis is that the EEG steepens the power spectral density, particularly in cases of deep sleep and unconsciousness yielded by anesthetic agents. So the experimental design for this study has been that 3 different groups of 5 people each underwent an anesthetic procedure designed to yield complete unresponsiveness. And at the end of the experiment, people were waken up and they were asked whether they were experiencing anything during the period in between. So this is how the typical EEG traces look like. We see that xenon and propofol both yield a lot of high delta waves, and ketamine yields some sporadic delta waves with increase in fast frequencies. So some of these results have been already presented in a paper by colleagues Simone Sarasso and Marcello Massimini, the last author, and they were specifically focusing on the TMS evoked responses, and I will tell you a bit more about it in the end of the first part of the talk. So here's how I quantify the spectral exponent avoiding peaks. So as you know, there are some typical oscillations that break this scale-free rule, for example, theta or alpha. So what we do here is to fit a first linear regression line in the log-log scale, and then consider the residuals. So when we find a peak, we consider that all its adjacent bins with positive residuals above a certain threshold are essentially part of the base of the peak, and those get to be discarded. And then, once we consider the remaining frequency bin, we fit a second line, which will give us the parameter of interest. So this, in the end, the slope of the second fit will be the spectral exponent. Now, when we apply this method to the data, well, we'll see in a second what happens with the method. This is just the power spectral density of the 3 different drugs, the grand average, and in green, the resting state prior to the anesthetic procedure. I made more transparent the peaks because those are not of interest. So I apply the same procedure on the grand average, and you can already see that the xenon and propofol are yielding a steepening of the PSD. So on the low frequencies and a more steep decay in the high frequencies, whereas ketamine has this somewhat mixed profile of an intermediate steepness and a flattening on the high frequencies. Now, when we apply the spectral exponent, we see that indeed there is a region around -1 to -1.5 that is occupied by all the wakefulness data points and by ketamine. And now, strikingly, when xenon and propofol anesthesia is done, the spectral exponent becomes much more negative, indexing a much more steep PSD decay. And when we lump together the participants and the recordings by the type of report we get, so either some kind of conscious report or a report of nothing, or nothing could be recalled, which we call no report, then we see that these two distributions are clearly different and separated. So this is good because it confirms our hypothesis. Now we actually delved a bit more into the data, but I'm going to skip this because of time. We basically applied the same procedure to two different bands and observed a characteristic pattern that was different for ketamine. But basically, when we considered both features at the same time, we were able to discriminate even better conscious reports from no report, and we are also able to differentiate ketamine from wakefulness, mostly because of its nearly flat decay in the high frequencies above 20 Hertz, from 20 to 40 Hertz. So we basically have not so much time to introduce to the concept of the TMS, but basically there is this algorithm that is able to compute the complexity of brain responses evoked by transcranial magnetic stimulation, which has been called Perturbation Complexity Index. And basically the idea would be that PCI is a measure that is maximizing the joint presence of integration and differentiation, and this is a theoretical requirement for the emergence of consciousness. So when we correlate the perturbational results with the spontaneous results, we see that there is a strong correlation that is mostly present in the 1 to 40 Hertz range, basically confirming that our measure has something to do with consciousness as this other theoretical measure has to do with. Okay, so consciousness can be present during anesthesia despite behavioral unresponsiveness, and the spectral exponent could discriminate conscious states, as wakefulness and ketamine, from states where consciousness was reduced or abolished, as in xenon and propofol. And loss of consciousness yielded a steeper PSD decay. And at the same time, we show that the spontaneous EEG, the spectral exponent, was predictive of the complexity of the EEG response evoked by TMS. Now, in the second part of the talk, I will tell you a bit about sleep. Basically, there are some similarities, of course, but most importantly, it is not possible to be awakened during anesthesia, luckily. Classically, there has been a mapping of similarities between anesthesia and sleep, and basically it seems the light phases of anesthesia are somewhat resembling sleep due to the rising of slow waves. In this particular data set that I reanalyzed, every person was going to sleep and was to be awakened several times during the night, and they were asked whether they were dreaming or not in the last bit they could remember. And then they were asked what was the conscious content. There were more questions about it. So we analyzed each 30-second prior awakening, and in this each chunk would belong to one sleep stage or to a different type of recall, so depending whether there was a conscious experience or there was no conscious experience, and somewhat intermediate type where consciousness, people had the feeling they were experiencing something but they could not recall what. So we asked again, is the spectrum steeper with sleep depth and unconsciousness? And well, the brief answer is yes. Indeed, this is a ground average power spectrum for the overall band and for the two different bands. And when we look at the spectral exponent, there is a nice progression going from wakefulness to N1 to N2 and reaching N3 slow wave sleep. And when REM sleep comes up, there is this intermediate, again, stage similar somewhat to wakefulness and N1. And then somewhat more complex patterns appear in the high frequency band of 20 to 40 hertz, whereas the 1 to 20 hertz behave mostly in a similar way to the 1 to 40 hertz. Moving on, there seem to be differences that are not purely related to the stage of sleep, but they are related to the type of experience. So no conscious experience versus conscious experience. And this was true, so we tried a classification approach, and we were able, with using spectral exponent, to classify whether a person had or did not have conscious experience, so discarding these no recall reports, across all stages, and even when looking at all non-REM stages separately. Again, in a nutshell, we see that in anesthesia, the unconsciousness yielding drugs were steepening the power spectrum of the 1 to 40 hertz with different effects in the two bands. We were able to predict PCI with the spectral exponent. And during the awakening, we had a progression going from wakefulness to REM1 to REM and N1, and then becoming more steep in N2 and then in N3. We had this pattern consistent with a flatter spectrum if the dream experience was present, and using the spectral exponent in the two bands, we were able to discriminate whether experience was present or not. So, going briefly over what this could mean, there was a presentation already by Wojtek that showed that essentially when in simulation as well as in real data, the spectral exponent or the PSD slope was able to track the excitation inhibition balance. Unfortunately, I will have to go briefly about it, but as you heard the presentation already, I'm sure that you can trust me on this. Basically, they showed that the spectral exponent was able to characterize the excitation inhibition balance not only in the model, but as well in real data. Macaques would track the anesthetic depth in macaques, and they were able to show that also spatially a larger proportion of inhibitory synapses would correlate with the PSD slope, and the PSD slope was actually indexing excitability over the theta cycle. Basically, this is what I told you already before. There seems to be more pathways to reach unconsciousness that are not purely by increasing inhibition, but when there is too much excitability combined with the inability to sustain it due to potassium channels being opened, then the system seems to collapse, and there is a similar PSD shape. The future direction would be to apply this method in disorders of consciousness and apply this method in brain stroke. Is it lower on the affected hemisphere? Briefly, yes. We did get some positive results. Preliminarily, we saw that the slope of the PSD together with the amount of alpha was able to discriminate people that were in a vegetative state from other participants that had differently gained degrees of consciousness. And indeed, we were able to classify with a nice accuracy whether people had or not the presence of consciousness. And overall, we saw that when a stroke would affect a hemisphere, the spectral exponent in that hemisphere would become more negative, indexing a more steep PSD in the affected hemisphere. So this is compared to the contralateral one. So this is just to say that the PSD slope is related somewhat to how affected the neural tissue generating oscillation is. And this is pretty much it. Just briefly, questions open and open matters is, does the 1/f signature is a sign that there is an optimal balance between order and disorder in neural dynamics? This is a provocative question. Why would actually a steeper PSD impair consciousness? And if we see stronger autocorrelation in the 1 to 40 Hertz range, does it mean that there is excessive order or regularity or stability, loosely defined? And would this stop local variation from spreading? Yeah, this is the framework I'm working on, but I have no definitive answers. But if the neural processing is tuned near criticality, as some people show, actually probably below the critical point in a slightly subcritical region, can the spectral exponent signal the distance from the critical point? Well, this is the framework I'm working on, and I hope that in the future we'll have more positive answers for these questions. So with this I want to end. I want to thank you in the first place for being connected from all over the world and following the presentation.